Hello, everyone, and welcome to Talk Nerdy. Today is Monday, February 23rd, 2026, and I'm the host of the show, Dr. Cara Santamaria. And as always, before we dive into this week's episode, I want to thank those of you who make Talk Nerdy possible. Remember, this show is and will always be 100% free to download as long as I keep making episodes. The way that we keep this going is by relying on the support of individuals just like you. I use Patreon, that's Patreon, as my sort of vehicle for that. So if you're interested in pledging on an episodic basis, as little as $1 an episode really does help to pay the I guess I shouldn't say the salaries. I'm not paying their salaries, but to pay for the hard work of my, coordinator / producer / assistant / she does everything for me, Noelle Dilworth, along with our incredible editing team at Warp Zone Post and, any other, hosting fees and things like that. So if you are interested in pledging, as I said, all you've got to do is visit patreon.com/talknerdy to learn more. This week's top patrons include Chuck Blell, David J.E. Smith, Daniel Lang, Mary Neva, David Compton, Brian Holden, Gabo J., Ulrika Hagman, Pasquale Gelati, and Joe Wilkinson. And apologies for my voice. I've been quite sick for the past couple of weeks. I think I'm finally coming out on the other side of it. But man, this cold is lingering. Let me know if any of you are dealing with the same thing. Not fun. All right. This week, I had the opportunity to chat with Laura Poppick. She's a science and environmental journalist. She's written for all sorts of, amazing outlets like the New York Times, Smithsonian, Scientific American, National Geographic, Wired, and a bunch of other places, Science Magazine. And she has a new book out, and it's really exciting because it is a finalist for a lot of kind of big deal awards, including the Los Angeles Times Book Prizes in Science and Technology, and also the Penn E.O. Wilson Literary Science Writing Award. The book is called Strata, Stories from Deep Time. So without any further ado, here she is, Laura Poppick. Laura, thank you so much for joining me today.
Thanks so much for having me here.
I'm super excited to talk about your new book. And right off the bat, this is so funny, but I would pronounce this word strata. Is that the actual accepted pronunciation?
That is how I say it, but that's been a common question. And it's funny because it had never even occurred to me that would be something that folks would struggle with. But it makes a lot of sense because...
Yeah, that some people might say strata maybe, but that's weird to me.
Yeah, and it's not entirely wrong. Isn't that how you pronounce the dish, the potato dish?
Oh, yeah, maybe. Yeah. But yeah, Strata, Stories from Deep Time. I'm really excited to talk. I think we haven't really done a good, solid kind of geology topic in a while, and especially paleogeology. We have sort of brushed up against these topics. Like I remember having a scientist on the show who talked about shark teeth and what shark teeth could teach us about time. And I definitely had a dendrochronologist on the show before, but I'm not sure we've ever gotten just really deep into, the stratification of the Earth itself, of rock, of matter, and what that can tell us. But tell me, first of all, because you're a science journalist, right? Did you get into journalism through J school, or were you a scientist first who made their way to journalism?
So yeah, I started in science just in my undergrad. So I did study geology in my undergrad and had the thought that maybe I would pursue that as PhD student, but I wasn't fully committed to that. So after I graduated, I worked in a geology lab as a lab manager, essentially just running samples. I was a field assistant, so I was out collecting samples with them. And it was in that time that I kind of decided that academia maybe wasn't quite where I wanted to be, but instead I wanted to be sharing all that this amazing, the amazing work that these scientists were doing in the lab. I felt like deserved to be given more airtime and have a broader audience. So it was in that time that I decided to pivot. And I ended up going to this graduate program at UC Santa Cruz that's designed for people like me who have a science background but less experience in journalism. And it's a 1 year
Cool.
long, very quick but intense program that really just whips people into shape and sends them off. And I had an incredible experience there and wouldn't probably have had the career that I've had so far without that.
I love that. And I think that that's such an important like step because we do tend to see, it's not always these two categories, but I've mentioned this on the show. We tend to see people who studied science and then found their way to journalism or science communication. And then we tend to see people who are trained in some form of journo or writing who then fell in love with science along the way. And I think, each approach, it's unique, but they do sort of overlap in a lot of ways. But one thing we can all agree on is that like we need expertise in science journalism. Like we cannot have the sort of trend that we're often seeing now, which is that general assignment reporters are being tasked with taking on science journalism and they just don't have any of the specialized training. That's a really big ask of them.
I agree. And yeah, and I think, as good as any journalist might be, I think having that background of knowing how to read an academic paper and kind of knowing that lingo and maybe knowing some of the dynamics within a field of science can help you report it better. So I think, I think there's always been this perception that science is not covered well. And I think that it's certainly true in some cases. And I also know so many, as you do, so many really talented science journalists out there trying to do this work who are currently doing this work. So there is such a mix out there. And my hope is for folks to be, willing to try to trust the journalists and they're doing the best that they can. And hopefully, I think that by and large, people are trying to do the best that they can. But as science outlets kind of shrink their staff and sometimes shut down, then it's becoming harder and harder to find that.
Yeah, or as science desks close, and then you've got like a politics reporter who's expected to go, report on something. I'm not saying they can't do it, and sometimes they do a phenomenal job, but it's a big ask of them. It's like if somebody were to say to you, hey, I want you to go down to the Hill, and I'm not going to have you report on this environmental topic. I want you to go down to the Hill and report on this like wonky finance topic for me. You'd be like,
and I would try to do that. I would do my best, but I would know that I didn't have the context. And I feel that way even with science journalism, which, I try to keep the types of stories that I write relatively broad, but I will never write like a neuroscience story or even really most health stories because that's not my background. And I know that I could write a story, but I wouldn't have the context that I feel would be really important to have for those types of stories.
Yeah, that's why probably the listeners also notice a big difference between when I have like physics folks on the show and when I do have more like medicine, neuroscience, psychology, because, the latter is my background and the former just isn't. So my questions are probably more naive. It's probably harder to get into the weeds because it's just not an area where I have expertise. And I will say geology is similar for me. When I was in college, not even grad school, I was obsessed. Well, I'm still obsessed with dinosaurs, but I took, paleo classes, and there was a big part of me that said, I'm going to become a paleontologist. And at the time, I didn't know that you could study like comparative anatomy and go about it that way. Most of the programs that I learned about were geology programs, which is still the most common way to get into paleo. And I'll tell you what, I took one geo class and I was like, nope, this is not for me. Yeah. It's interesting, but it's hard. And so I'm really curious, what is it about geology that sort of got to you?
Yeah, it's a good question. And I think there are so many things about it that I fell in love with, but it kind of took me by surprise because I had never taken a geology class before going to college. I never took earth science or anything. And I only took my first geology class kind of just on a whim because a geology professor at the college that I went to was friends with a high school teacher that I had. And so that teacher said, when you go to your Bates College is where I went in Maine. When you get to Bates, you got to meet this guy. And so in the first couple of weeks of college, I met him just to meet him. And he was like, well, when are you going to take a geology class? And I kind of took, I wasn't really planning to, but I took that literally and was like, okay, well, let me look at the course catalog. And I noticed that the classes were largely outside, which appealed to me. But I was also, I was going into college interested in environmental science. I thought maybe I'd be an environmental science major or biology major or something like that. But I was specifically interested in climate change. And I noticed that the geology department at my particular school focused a lot on climate stuff. So that pulled me in. But then once I got there, I just found, it to be just such a dynamic science. We got to carry around like tool belts full of little bottles of acid that we got to drip on rocks to see if they fizzed. And we got to bring around colored pencils and magnifying glasses. And it just felt like glorified kindergarten sometimes. We were just like pulling around these tools and like collecting data just by looking at things out in the wild. It was just very fun. So I liked that piece of it. And I also I really appreciate the really big picture that it allows you to take. I think I'm super fascinated in biology and the natural world, but when you get into the real nitty gritty stuff, I lose focus. I find that I focus best on really big picture systems. And that is what geology often is. I mean, you can get into the nitty gritty too, but what appeals to me about Earth history, specifically as like an element of geology, is that it not only takes a big picture of the entire planet, but it takes a picture of the entire planet in its entire history, which is, a huge view. So it just changes the way that you see the world. And that's another thing that I write about in my book, and that helped kind of me fall in love with this field of science, is that it truly enhances your day-to-day experience when you can look at the world through a geologic lens.
I love this kind of concept of deep time, and I want to get into that, but I have to ask just like a silly question. You were saying that you're encouraged to, use these little bottles of acid, and you have your little tools and your colored pencils. And so many geologists that I've talked to and paleontologists, one of their favorite tools to use is their tongue. And I'm curious if it was ever encouraged or if it was discouraged for you when you were in the field to like lick rocks.
I've definitely licked rocks before. I've done that. The most recent, occasion was actually writing this book. I licked some dinosaur fossils.
Nice.
There's like licking a fossil so if you kind of suck on it a little bit with your tongue and it feels a little sticky, then that means it's porous, which means that it's a bone, as opposed to a rock would just be smooth. So that's one iteration of the lick test, but there's another lick test where you just kind of put some sediment on your tongue and like rub it around on the roof of your mouth. And if it feels gritty, then you basically just categorize it as gritty silt or something, whatever it might be. So you do the lick test both on solid rocks and loose material, depending on what you're studying. And I love that too. It's a full sensory experience.
I actually I saw a periodic table once that I was very excited to get for one of my super nerd friends. That was it was like the full periodic table, but it was just, can I lick it? And it was categorized by what elements you can lick.
I love that.
Yeah.
Genius.
And I have to, so everybody listening, I shouldn't say everybody, but those of my listeners who have been around for a while, because we're like on episode 500, I don't remember, but I've been doing this a long time. They know my little guy Killer, my 15-year-old dog who is asleep next to me on a sheepskin. And I have to at least bring your pup into the conversation, mostly because I can kind of hear them dancing around, which is fine. But I want to make sure that they get their fair, recognition. So who's with you in your office right now?
Yeah, of course. He does this sometimes. The moment I start talking to someone on the phone, he bounces around with his tennis ball in his mouth.
Yeah, because he wants your attention. You're not paying attention to him.
I'm not.
What's his name?
His name is Aster, which is after the flower that's native to New England up here. He's got a light blue eye that kind of reminds me of aster flowers.
Oh,
I say eye singular because he has another eye that's green. So he's two different
cool. Oh, is he like a husky or like some sort of sled dog?
Yeah, he's got husky in him.
Nice.
Yeah.
What a good boy.
Good boy.
How old is Aster?
He's almost 4. But, it's been quite cold here in Maine the past few weeks, so we haven't been able to go on as long of walks. So he's a little bit more energized these days.
I can imagine. Yeah, my little guy Killer is 15. He'll be 16 in May. So he sleeps 22 hours a day. And like, although he still has enough energy, he can climb the stairs. And, my dog weighs 9 pounds. So I'm proud of him for being able to,
So
to still get
cute.
around, but definitely doesn't have the energy of Aster.
No.
So let's get into it. Let's talk about deep time. This concept of deep time is really fascinating to me because I think one thing that I guess I didn't realize, and I have to still remind myself of very often, is that the Earth is in a lot of ways almost as old as the universe itself. And so when we talk about studying the Earth, we're going back real far. And I think when I was younger, or I don't know, even today, I have these moments where I have to realize it again, that like, there's not like just tons and tons of time before when the Earth was formed. There is some deep time before when the Earth was formed, but not that much, right?
So the Big Bang, though, was quite a bit before Earth.
What was that,
formed.
like 13.8, if I'm remembering?
I can fact
Yeah,
check.
I'm Googling. Yeah, 13.8 billion. And then Earth
Is
age, how
4.5
old is the Earth?
billion. So it's impossible.
Okay, yeah,
to
I guess that is
wrap
quite a
around.
lot.
It is, but to your point, I mean, in the scheme of things, it's hard to actually make sense of what that even means.
Right. It's like what, like a third of the time that the entire universe has existed, our own planet has existed,
Yeah,
which
I
is
would
pretty
think
nutty if you
it's
think about it.
significant. Yeah. I never actually, it's funny that you bring this up as your first kind of question about deep time, because in the whole process of writing this book, I thought basically not at all about the time before Earth formed. I was just so focused on
Oh, I
Earth
love it.
itself.
Yeah, because Earth is really, really old. And I think like it's kind of hard to fathom what 4.5 billion years is, the same way that I think, and not to get political, but how can you even help it at this point? The same way that I think a lot of people don't really understand the difference between like somebody who has $1 billion and somebody who has $1 million.
Absolutely. Yeah. It is very hard to wrap your mind around it, which is one reason why I start the book with an illustration that I had a friend of mine draw. Well, she's a very talented illustrator and also happens to be a friend of mine named Sarah Gilman. And she drew this diagram to help folks understand how the 4 different periods that I write about in the book relate to each other in time. And I used
Mm.
this method that I honestly don't remember the first place that I learned this, but I learned it at some point in my education in geology, which is that if you kind of stretch your arms out, in fact, I think John McPhee also has an analogy like this too in Basin and Ranger, one of his books. But if you stretch
Hmm.
your arms out and imagine the span of your arms as the entire span of Earth history, so 4.5 billion years, and let's say your right hand is the beginning of Earth and your left hand is now, then humans have only been around for like the amount of space that's like the white part of your middle finger nail, like tiny, tiny amount compared to your entire arm span.
Wow.
And if you want to think about other events, like the first one that I write about in my book is the rise of oxygen gas in the atmosphere. That doesn't happen until around your heart, so around halfway through. And I find that exercise to be very helpful in feeling like at least an embodied sense of time, so that you can kind of
Hmm.
stretch your arms out and think about where your heart is and think about from your heart to the end of your right hand and think like all of that time, all that space, there was no oxygen in the atmosphere, which means there was no life that was more than one cell, and the earth just looked entirely different than it does today for, more than half of its existence, essentially.
Oh, this is incredible. Ice doesn't come until we get to our wrist, on the other hand. I mean, that's amazing.
Yeah, and to be clear, there the ice like section is about the coldest period on Earth. There would have been ice before then, but that is the coldest period on Earth, and
That's when we were just like all ice.
when the planet was covered entirely
Yeah.
in ice. And what is kind of shocking about that is it's not until after that event that you start having animals that we recognize as kind of similar to the animals we have today. So for the majority of Earth's existence, there have not been creatures like the ones that we know today. There have not been plants. For more than 90% of Earth's history, there were no plants on land. Just massive periods of time without these recognizable inhabitants of this planet.
That's so cool. I have a dear friend who's another science communicator named Trace Dominguez, and he has a tattoo. It's so funny that it's like, because you're talking about deep time, and his tattoo is sort of about deep space, not completely. It's really just about our own solar system. But he does the same mapping across his arm for our solar system to really try to help people understand how far away from the sun certain things are, and just how the gas giants, they're way out there. The inner planets are way closer together than we think. And it's funny because I think we're often taught using, I guess it's the tools that we had at the time, or maybe people weren't thinking about scale very much, but we're often taught using scales that are easy to see. And so because of that, the distances get lost and everything starts to look equidistant. But that's really not how time or space works. It's like a whole bunch of stuff that we know that's relevant to us is like clumped together really recently.
Yeah, absolutely. There's this incredible, I guess, I don't know if you would call it like an exhibit. It's out on a highway in eastern Maine, and it's a scale of our solar system, that on a highway that you like drive past Mars and then however long, and then it's like over the course of several miles that you hit all the planets.
Wow.
And I just thought that's genius. And now that you're talking about this, I'm like, oh, you could do something similar, but for events in Earth history where you're driving, you're like, oh, it's not until now that the plants came. It's not until now that we had oxygen or whatever else it might be. I love that idea.
Oh, I love it. Yeah, that's great. Because it's any way that we really are. And this is me as a psychologist kind of, I don't know, just talking out loud here, but we really aren't good at scale. Like it doesn't feel like an innate ability that human beings have, probably likely because through most of human evolution, we weren't thinking about extremely large or extremely small things. We were thinking about things that were on a human scale. And so once we start really talking, and we could be talking about risk when it comes to financial decisions. We could be talking about health. We could be talking about, as we mentioned, deep space or deep time. But when we start getting outside of the human scale, it's so hard to wrap our heads around these things.
It is. And part of the magic of kind of sitting in the space of deep time in this case and kind of looking at the world through a geologic lens is that I think you can, to a certain extent, there will always be limitations, but to a certain extent, you can start kind of training your mind to think a little bit differently. It's almost like an exercise that I honestly, when I was really in the thick of writing my book, I felt it more viscerally than even now, having not been as steeped in the writing process. It doesn't feel as clear to me. But when I was in the thick of writing the book, just entirely immersed in these episodes that were hundreds of millions or billions of years ago, I could feel more clearly how recent like the last ice age was, which was, it ended maybe 11,000 years ago, at least where I am in Maine. And people would ask me when I asked, I maybe would mention that I'm writing a book, and they would say, what is it about? And I said, major events in Earth history. And they would say, oh, like the last ice age. In my mind, I'm like, no, that's so recent. I don't even consider that Earth history. And it's like recent history, but it's all relative.
Yeah. Yeah, we've been around for what, like 200,000 years? So, yeah, if people have been around, it was not that long ago. But It is crazy to think about the fact that, a person, I guess, to a person, a century is a lifetime. And so
right.
A millennium is pretty hard to fathom. And anything beyond that is
millennia. Yeah. But geologists, so when people think about deep time, I think some people are like, oh, yeah, deep time, as in the last ice age. But a geologist who studies, events way before that are like, that doesn't even count as deep time. That's not what we're talking about. But what I love about deep time as a concept is that there's no like definition of when deep time starts. And from my research of the phrase, I found that it wasn't even coined by a scientist, but it was coined by John McPhee, an author who wrote Basin and Range in 1981. And as far as I could find, that was the first time the phrase appeared. So he used it as a metaphor.
1981.
Yeah. Yeah.
Wow, that's recent.
It's very recent. And now it's used as a scientific term, but it was created by an author, which I think is so fitting for Earth history because it is such a, I mean, John McPhee says it himself that it's sort of like the humanities of the sciences because you're coming up with these narratives from the past that you have some scientific evidence for, but you're also needing to use your own storytelling skills to kind of pull together. So it feels so fitting that an author, is the one who coined that phrase.
So when we think about geologic time, obviously geology is the thing that helps us measure these things. And that question of how do we know what we know? Well, geology involves rocks, right? But were there always rocks? Like when Earth was first formed, did we have rocks? Or does geology really start with the first rocks?
So that's a good question. And so Earth itself would have always had some sort of material that is solid, right?
Mm-hmm.
But the rock record, which is essentially like what's available today to look
Right.
at in terms of what's left on the planet, is limited to more recent history. So the very first kind of rocks, crust, minerals that would have been on, the very young Earth have over time kind of gone through the conveyor belt of plate tectonics, which, through time, plates get pulled beneath other plates and they get melted and recycled back into the mantle over time. And so for the first while on Earth, there were rocks, of course, but we don't have them anymore. They've been erased. And so
Right.
the rock record is, you have more rocks available for the more recent, time intervals. And so the very first episode that I write about in the book, which is the rise of oxygen in the atmosphere, it happened around roughly 2.5 billion years ago, which is halfway through Earth's existence. And it's still relatively hard to study because there are only a few places on the planet to find that you can find rocks of that age. It is just still quite old. And so there are a few places on the planet that have what are called cratons, which are these like stable pieces of continents that somehow have been sheltered from the events of plate tectonics, plates getting pulled back into the mantle. And so they preserve these really old minerals. There are other places that have older rocks than the rise of oxygen. Parts of Canada have really old rocks, parts of Greenland, but they're few and far between. And so geologists have to get kind of creative in how they study these ancient events because the further back you go, the fewer rocks you have to work with.
And even in terms of the first person who figured out that location, was relatively unscathed, at least within the past 2.5 billion years. How do we know how old a rock is?
Great question. So there are a number of different ways that you can figure out how old a rock is. For rocks that go back 2.5 billion years and, rocks that are similarly old, there's one particular mineral that is probably the most popular mineral that's used to date a rock, and it's called zircon. There are these tiny little crystals. They look almost like a quartz crystal, but they're not. They are something else. They are zircon. And zircons contain just little trace amounts of uranium that decay to lead over time. And so you can use that kind of clock of uranium decaying to lead to figure out how old a zircon is by putting it into a machine, blasting it, and finding out its uranium to lead ratio. So when you do that, you figure out roughly how old the rock is that zircon was in. And by the way, if you want to get into how you get those tiny crystals out of a rock, I can go all the way into that too, because I did that for a year when I worked in a geology lab. And it's
okay. You have to actually physically remove them from the rock?
Yeah. So it's it's a whole process. So I had worked with a group of geologists at Princeton University who were studying a period that I write about in the book called Snowball Earth. And I had gone to South Australia with them as a field assistant to collect sandstones and other samples of rock to bring back to the lab. And there were certain rocks that, for a few different reasons, these researchers thought might contain these zircons that are such powerful kind of timekeepers for the planet. And so we brought a bunch of those back, and we're talking like rocks the size of, they were like, small boulders. They're the size of my head, the size of my hand. These are, big rocks that we need to somehow pull out a mineral the size of like a grain of sand, tiny. So you put it through a series of machines that crush the rock first into kind of pebbles and then into sand bits and then into finer bits. And then you put it on, at least this is how it worked back then. Maybe the technology has changed since then. But when I was working in this lab, you then pour the sand onto a table with water, and the table shakes and it kind of sorts the sand, sort of like at the edge of a beach. You might find a dark rim of sand and a light rim of sand. And that's all based on the weight of the sand, the density of the sand, because it's all sorted based on when it gets laid out by water. So we recreated that in the lab. And then the zircons are super dense. So they are like, create this very distinct band, and then you collect them in a little cup, and then now you have them available to kind of push through the rest of the process. So it's very labor intensive, it's expensive, so it's hard, and you don't always find a zircon. So all that's to say, these are the materials that we use to date rocks, but you can't always find zircons in every single rock that you study. So what you have to do is date as many rocks as you can, but then by using geologic mapping and trying to like figure out what rock might be equivalent, across the canyon or across the country, wherever you might be, you can start to draw connections and kind of estimate the age of a rock, even if you don't have material to date precisely.
I mean, it's pretty incredible that we even were starting to be able to determine the age of the earth or the age of different rocks, like coming on 75, almost 100 years. I mean, I guess it's it's 2026 already. Geez. And I think that some of these, I've just been Googling some of these like ages or these techniques for developing and understanding these ages were kind of mid last century. And we have, I think one of the things that maybe is a huge misconception for a lot of people, because when I said, how do you know how old a rock is? And you're like, obviously it's the zircon. I think a lot, you didn't say it that way. I think a lot of people were like radiocarbon dating, but it's like, no, that doesn't work for things that are older than like, I don't know, 50,000 years.
Right. People think about radio, which is very helpful for more recent things, but that doesn't work for much older material.
Yeah. So there's a lot of different approaches to date or to age things, right? But they probably become pretty reduced when we're talking about things in the billions of years versus things in the millions or even hundreds of thousands or thousands of years.
That's right. But this is where strata comes in handy. So stratigraphy, which is the study of these layers of rock, is the study of kind of areas on the planet where you can find these vertical expanses of strata, of these layers that are essentially like barcodes on the planet. And so when you study, and when you take what's called a stratigraphic log, people call it different things, but let's call it a stratigraphic log, where you're studying, let's say, a canyon wall, and you are taking centimeter by centimeter observations up this canyon wall with these layers. And then you're doing that again a little bit down the canyon or wherever you might be. You're collecting barcodes of the planet, and that allows you to do the same thing that dendrochronologists do sometimes, which is look for similar patterns, and you can kind of cross date. You can find these dates across, the expanse of the planet, which I find really beautiful, that you can start to make sense of these patterns, which requires people to be doing the work. Like I think about the very first geologists who started trying to make sense of Earth history. They had no material to work with. They had to create the first geologic maps and the first stratigraphic logs, and they were working, with nothing to compare to. So it is such a collaborative, all science is collaborative, and especially this field of science where you need people to be adding and adding so we can have material to read from when we're trying to pull together these stories.
I love that. So much of uh, what's it called? Stratigraphy?
It's stratigraphy. It's not the easiest word.
Stratigraphy. Cool. Stratigraphy. So much of stratigraphy is like validation of other measurements and this big pool of data where each new sort of observation, maybe not each individual, but groups of observations are not only validating older observations, but also allowing to refine the I guess the data even further.
Yeah, that's right. And what's really cool too, at least from my perspective, because I still can't get enough of this stuff, even though I've written a whole book on it. I'm still not sick of it. You can, one person might look at stratigraphic logs and they're really interested in the dates and the age, but someone else might look at the chemistry and look at, okay, how are the oceans changing over this time? And someone else might look at what pollen was, or like what plants may have been alive in these different periods. Like there's so many different ways that you can look at the layers. There's not just one way. And it might be something you can see with your naked eye, it might be something that's more chemical and that you have to put through a machine. But there are so many layers within the layers of stratigraphy. See, I still struggle to say the word too.
It's a tough word. Yeah. So how does it relate, I guess, to, like you mentioned, and it's a great visual, like a canyon wall, like, and we've all experienced that when we've visited these kind of geologic wonders, or even just out and about on a hike, if you happen to live in an area where there's a lot of sort of, I guess there's a lot of relief, right? A lot of like natural phenomena. You'll see layers, and you'll see different colors, and you'll see different textures. How does that relate to like people who study ice cores, for example? Is it basically the same thing, just using different techniques?
I love this question. And someone asked me this yesterday at an event I did, which was the first time I heard it. So I love that it's coming up again.
Oh, nice.
Yeah, you're exactly right. They're basically doing very similar things. An ice core is taken so that people can look at layers of frozen water through time, and they're taking chemistry from the ice cores to understand changes in the atmosphere, the ocean, whatever it might be. And yeah, they're looking at layers to understand change through time, which is exactly what stratigraphers do in rock. And then I will say that there are also geologists who study modern Earth. They don't even necessarily study rocks, but you can do the same thing in modern sediments. Like you can take a core of mud from a lake and you can study more modern history. There's so many different ways to do this, but in the book I was looking at rock. But yeah, there are many different types of ways to study layers of the planet.
And then what about loose rocks themselves? Like you mentioned these boulders that you guys were doing some obviously zircon testing on. So that's a way to figure out how old they are. But can an individual rock tell you much about change over time? Or do you really need like a big chunk of the side of a mountain or the side of a cliff or something like that?
So, and just to be clear here, so that a boulder that we would have collected, we would have like hacked off we would have known where it was in the bedrock. Because if you just take a boulder or like some cobble or whatever off the ground without any knowledge of where it came from, then that doesn't really help you very much. So we did.
Gotcha. So you need the like in situ context to understand sort of the geology of what's going on. Okay.
So, and I would say there are some kind of atypical rocks that maybe you could glean something incredible from a single rock. But for the most part, you need these, many different barcodes, let's call them, to really make sure that you're telling the right story, especially with these types of layers, which are layers of sand and silt and clay that are the kind of the particles that make up sedimentary rocks. And, they can basically arrange themselves in a way that to your eye, you're like, oh, that's obviously a landslide. Like it looks like it's a mess. It looks like there's just a bunch of sand and grit and everything. And to my trained geologist eye, that's clearly a landslide. But that very same pattern could be actually the result of like a glacier dropping or melting out some sediment that had been floating around in an iceberg. So there are these different kind of observations that you can make that can lead you astray, which is why it is really important to take a whole bunch of observations to start to really pull together a whole story. But there's always the odd observation that blows everything, out of the water and kind of rewrites some sort of narrative.
It's such a good sort of allegory. I don't know. It's just such a good example of the way that good science does function, right? Where individual discoveries, although they tend to be what gets the most press and they tend to be the flashbulb moments that people remember, they're actually not very important for telling the story. The story only starts to emerge through the slogging of like thousands of individuals who are working their asses off to uncover this little piece and compare it to all the other people that are doing it as well. Like, good science is not a series of aha moments. Good science is a ton of information being constantly compared to other information to build out that tapestry. And like, you just couldn't do geology without that, could you?
You really couldn't. And you couldn't do geology without collections of humans who are willing to do work that they know they won't like fully get the answer to in their lifetime, right? Like they have to do this work to add to our kind of pool of knowledge. But, the folks studying, why oxygen arrived when it did, or why, animals evolved when they did on the planet, they probably won't know for sure in their lifetime, but they are okay with that, presumably, because they're doing the work, maybe in part because geology also gives you a sense of your own smallness, right? So there's in kind of egolessness that you kind of have to take on if you're studying the vastness of Earth history, because you recognize how tiny you are and how tiny your life is in the span of everything. And maybe you find like a little bit of joy in that. That's something that came up a lot in my interviews, is that it kind of forces you to be humble and to check your ego, because we're such kind of temporary visitors here.
And I love that your approach, as you mentioned before, kind of starting off with the earliest rocks, but then with like oxygenation and the drawing that you spoke about, you sort of went through your writing in a way that's so beautiful, where we think about, obviously chronology makes sense for talking about deep time, but I love how you divided it out into these 4 sections, and they correspond with the image that you described right at the beginning: air, ice, mud, and heat. It has very Captain Planet vibes to me, which I love. It's like form of mud, our powers combined. But it is really cool, this idea of these sort of important major turning points in geologic time. But of course, those stories couldn't be told without, and this is what brilliant science communicators do so well, so I thank you for continuing in that tradition, without the stories of the people, as you mentioned. And so you were able to visit different laboratories, different field researchers who were working towards answering at least a portion of these big picture questions. And along the way, you share not just the stories of what we know, but of course of how we know what we know, but even, I think, in a lot of ways, more importantly, who are the people who are showing us how we know what we know. So I'm hoping that here, kind of in the last bit of time that we have together, you'll share maybe some of the stories that were like the most salient for you, or like the trips that you went on that were the most fun or the most harrowing, or just the things that came up for you while you were out and about learning from these brilliant minds.
Yeah, it was really important to me that I kind of include humans in the book. And just to the first point that you made, which is that you kind of rarely have maybe geology writers on your podcast. Mm-hmm. I think in part that's because there are just fewer geology books out there compared to other fields. And
it's the same with math. It's like math, geology. Like those are even on my bookshelf, there are fewer of them. And I'm always like, oh, we got to like represent in STEM in a different way. It doesn't always lend itself, I think, to I don't know. Maybe it does lend itself to more stories, and there are just fewer people digging into them.
I think that's it. And that's kind of what
Mm-hmm.
motivated me to write the book, is because I had this experience in geology labs. And I got to tell you, geologists are a lot of fun. And I feel like people deserve to know that, and so that's part of
Mm-hmm.
why I wanted to write the book, was because I felt like there aren't enough geology books out there. And so in making that decision, it was important to me to include some of these characters.
And how did you, I guess I want to know, even before you get into some of your favorite stories, how did you choose who you spoke to? Was it important to you to show diverse representation in the book? Was it important to you to say, no, this was a discovery that was important, I want to find the person who made that discovery? Or this is a really interesting technique and I want to profile the person doing this technique? Like, what was was it bottom up or top down, your approach to finding these characters?
It was kind of honestly all of the above.
Mm-hmm.
But and it was really hard to decide, because there are, dozens or hundreds of people studying these events. And I know that I missed out on, I'm sure, so many wonderful humans that are doing this work. But at a certain point, you have to make a decision. And so often I would find a very compelling paper that was some sort of breakthrough discovery, or maybe some breakthrough claim that people weren't necessarily willing to believe, but that they were debating. Who I was trying to find who seemed to be central to some of these debates, and I went after them, while wanting to make sure that I represented all the different types of folks who are in geology, because it can kind of seem like it's only maybe older white men traditionally are folks that were, for a while, those were the folks that got the jobs and all this, but there is slowly over time, there has become more diversity in the field. So I wanted to make sure to represent that as well.
Yeah.
And also, who would be up for being in a book. I think not everyone would be up for that. And
Right.
I got really lucky to find people who were really generous with their time and were up for helping me kind of convey their science, to a lay audience. And yeah, in terms of a favorite trip, there were so many wonderful moments.
I know it's so hard. It's like, and I never know what to ask either. It's like, what did you discover that you didn't know? Or like, where did you go? That was surprising.
Yeah,
It's because what superlatives are tough when like everything was awesome.
Everything was awesome. I will say I had this kind of serendipitous moment that I mentioned in the book. But I was in Minnesota for the oxygen section of my book. I was doing research for that. And then I happened to go to a lab in the Minneapolis area just to meet someone who may or may not have been in my book. He ultimately was just a little bit. But at that lab, I ran into a geologist named Paul Myro, who I had known of because of my time in working in the lab at Princeton, but had never met. But I knew his face from the internet because I'd been looking up his research to figure out if I wanted to reach out to him about his work, and I decided I did, but I hadn't yet. But I just saw his face, and he was just at this lab, and I was like, "Are you Paul?" And the point of the story is that, so it was him. We chatted, and I mentioned to him that I wanted to try to get to Newfoundland because some of the oldest animal fossils on the planet are there, and there are rocks from this period. That's kind of the end of the snowball Earth era that I wrote about in the book. That are in Newfoundland, and I wanted to get there. And without really knowing much about his background at all, I just asked him, "Do you know anyone, or do you know, anyone I can connect with in Newfoundland?" He's like, "Oh, I'm going there next year. Maybe I can see if you can come with me." And so, just that chance encounter made it possible for me to go with him and a group of scientists and students from Syracuse University, and we were out there the next year. And he was super familiar with that area because he had done his PhD out there. So not only was he going on this trip, but he was deeply familiar with these rocks. And so, he's a wonderful geologist and very fun to chat with about what he knows about the rocks. And he's super comfortable out there. So there was a lot of like driving on, I don't know. There was one moment where we were driving on a dirt road where it's like, should we really be going all the way like down this very like seemingly not maintained dirt road? And we ended up backing up quite a bit, just like trying to get ourselves out of what could have been a situation. And we were totally fine, which was great. But there are those moments when you're in the field where you're like, okay, I'm just going to trust, like he's been here, he's done this field work for decades, and I'm just going to trust this. And that's part of the fun of geology fieldwork is that you get to spend time with these people who just, know these kind of remote areas so well because they just return year after year to do their research there.
Yeah, I was going to say part of just choosing the stories that you tell, obviously is identifying folks whose voices historically may not have been represented, having chance encounters with people and being able to go out into the field with them. But so much of geologic work is geologically tied, right? So like maybe somebody's lab doesn't happen to be in the same place where they do their field work, but maybe their lab is, in a place where there's like a rich deposit of certain types of rocks or something like that. But so much of geology is like going to the place, right? And so that's how you have to tell those stories.
Mm-hmm. It's true. I think it's hard to choose your studies based on the rock around you because it's limited. And even if you study that rock, you'll probably have to study a rock somewhere else to make sure you're understanding it correctly. So there is a lot of kind of traveling around, which is fraught in its own way. I think geologists think about this where they're like, okay, we're going to burn all these fossil fuels to get to the places to study how climate has changed in the past to understand how it might change in the future. It's all kind of tied up in this knot that I think people try to work through and grapple with. But at the end of the day, the opportunity to know the earth more intimately is just such a privilege.
Absolutely. And even though I could totally end on, because that was such a beautiful button and I could end on that point, you also made a comment in there, which I think brings us full circle to the beginning of this conversation, which is that you originally studied geology and you originally were interested in exploring more about our planet because you were interested in climate change. So I was hoping maybe you could share a little bit with us right here before we say goodbye about how studying deep time relates to our understanding of both historical climate change, but also what we are doing to the planet now. Like, what do you have any sort of insights on that, or things that you hope the readers will get from the book as it relates to climate change specifically?
Yeah, I think it's a super important point to make, because I think that it can sometimes feel like studying Earth history is just like burying your head in the sand and not even, you're just thinking about these esoteric questions that have no, consequence in our lives today, which sometimes, maybe on some days, they are esoteric questions. But in the broad scheme of things, the reason that we're doing this is to understand the planet better. And the events that these scientists are studying are events of change. Like this is, scientists have to get grant funding, and the grant funding goes to the superlatives, the periods of big change, and for the most part. And so through the study of the planet's past, we get this sort of blueprint to understand the complexity of what we call the Earth system. So all of these loops, these feedback loops that balance the Earth as it goes through these changes, whether it's a climate change, whether it's changes in who's alive on the planet, the Earth, has ways to bounce back, to heal itself. And so when we think about the present and the future, we have this whole blueprint in the past. And it's thanks to that blueprint that we understand how unusual the rate of change is today. So that's really important to point out, that we might not know how shocking it is, how quickly the Earth is changing today if we didn't have the past for, to give us that context. We also can look to the past to understand on geologic timescales how the planet balances itself out, which is really important because we can't just look to the past 100 years to think about what the future of Earth will look like, because that's just such a small sliver of the bigger arc. So you need to be able to look to the broader arc to understand, where the future arc is going, and to understand how our actions today will impact the planet, because some of the responses of the planet will be delayed. And we know that because of the rock record. So there's just such a richness to the information we can glean from the rock record. And more, I think there are geologists who are trying to advocate for that, to continue this work so we can get to know the planet better.
Oh, it's so important. It's fascinating. And I'm so glad that you took the time to compile all of this really interesting knowledge about these 4 kind of important, I guess, I don't want to call them moments because they're definitely not moments in geologic time, but these 4, what would you call them?
I mean, I call them moments in the book, but I guess it's
I love that. Okay, good.
like a lyric,
It's not me.
phrasing. But in geologic time, a couple 100 million years is a moment. They're events, they're episodes.
So true. Thank you. That was very validating. Thank you. But yeah, taking the time to do this this important work and to kind of couch these things in a way that is not just much more understandable, but also brings it to life through these important stories. I think it's so important that we continue to learn, that we continue to be curious. And your book is, it's a tool that a lot of us can use, especially against the background that we're dealing with right now. Maintaining curiosity and learning about the world that we live in. It's actually not just, I think, good for our brains, but I think it's good for our psychology right now. It's healthy for our mood, and it's healthy for us as a culture. And so I'm just so glad that you were here with us, that A, that you wrote the book, but B, that you took the time to hang out with us and share some of these really interesting insights. So thank you for that.
Thank you. It's been a pleasure chatting with you.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.